Hi everybody, Kurt here. So if you've been following me for any length of time, you'll notice that I've been starting to get into solar imaging. So I started this about 4 years ago with this telescope right behind me. It's my old Orion ED80 f7.5 and it's 600 millimeter focal length. And I purchased a Quark to do the solar imaging with it. And I promptly went out and purchased this camera right here. It's the ZWO ASI178. I saw that other people were using it for solar imaging. It was relatively inexpensive. They were taking some good images with it, so I figured it'd be a good fit. And I started imaging with it, and I was really happy with what I was producing 4 years ago, and it was great. I was like, all right, cool. But then, for whatever reason, I got out of solar imaging. I just stopped doing it for whatever reason. I got sidetracked. So I did nothing until now. This year I'm starting to get back into it again. I started doing some research before getting back into it, and I realized that this ASI178 may not have been the best choice for a camera to use with this setup that I have here with the Quark and the ED80. So I found out that this might be a better camera to use. This here is the ZWO ASI174. And you'll notice this little thing on here, this other thing, it looks a little different. It's actually, this thing's a tilt adjuster. I actually purchased it when I bought the 178 as well. What the tilt adjuster does is most solar imaging cameras, you might see these rings around on the sun. Those are called Newton's rings, and what you have to do, you have to slightly take the camera off the center point, and that'll prevent those Newton's rings. They're about $200, something like that. I think this one was only $100, and it's pretty simple to use, and it does a great job. Some other cameras have a tilt adjuster built in. So what I want to do is I want to do a comparison between these two cameras. What I want to do is I want to show you a table that has all the specs in it. I'll go through those, and then I'll show you some actual images that I took with both sets of cameras, so you can compare them yourself. I'm Kurt Zepatello, and you're watching AstroQuest 1. Okay, let me go through my setup before going into that data table. Okay, as I said before, this is my Orion ED80 f7.5 600 millimeter focal length refractor that I'm using for my scope. It's sitting on top of my ZWO AM3 mount. I love this mount, it works great. It's very compact. But I didn't have this 4 years ago, so that was a big difference. 4 years ago, for my mount, I was using the Orion Atlas Pro, which is another very good mount, but it's much bigger and bulkier. Now, let me show you this Quark in a little bit more detail. Here it is. The Quark is an eyepiece Etalon HA filter. They call it an Etalon filter, these filters that are used for looking at the sun. This is the Chromosphere model, so it's specifically designed to look at the chromosphere, although you can use it to see prominences, and it works very well for that as well. One thing about this Quark is that it's also a Barlow lens. It's 4.2 Barlow. So what does that do? That turns the focal ratio from f7.5 to 31.5, and the focal length, it was 600 millimeter focal length, but with using this Barlow, it's the equivalent of 2,520 millimeters. So it makes the field of view much more narrowed, but you can see much closer into it. The other thing I want to say about the Quark is it comes with an end cap for protection. Make sure you take this end cap off when you use the Quark, because if you don't, the full force of the sun comes through the telescope, hits it diagonal, and is going to hit this end cap. And what's going to happen is the end cap is going to smoke and start to melt. It's going to do this. How do I know? Because this is what happened to me recently. I've done it. And fortunately, it worked afterwards well enough. However, when I brought it home, I did notice there was some film on the diagonal, and there was a little bit of film on the bottom of the cork. I cleaned the diagonal up pretty well. That was no problem. But DayStar, the manufacturer of Quark, recommends, don't clean this, send it back to them. So I called them up and explained what happened, and they were laughing. It said, yeah, it happens all the time. He said, look, if you feel comfortable cleaning it yourself, you can do it yourself. They recommended using 91% isopropyl alcohol with Q-tips. I promptly did that, cleaned it right up, and it works even better now. Okay, well, let's go take a look at the data table, and I'll go through some of the specs with that. And then I'll show you some images that I've taken with both cameras in the end. So let's take a look at some of these specifications. First one I want to look at is frame rate in frames per second. And for the ASI174, it's listed as 128 frames per second at 12-bit. And it's also listed as 164 frames per second at 10-bit. Basically, you want to have the highest bit possible. It gives you a better dynamic range. And ZWO lists the ASI178 as having 30 frames per second at 14 bits and 60 frames per second at 10-bit. Just to let you know, I was not able to get anywhere near these frames per second with my cameras doing testing. At 12-bit, I was able to get about 70 frames per second maximum. For the ASI178, I was able to get like 26 frames per second. However, the 174 was clearly a higher frames per second, faster frame rate. So that's really good, especially for solar imaging. Resolution in megapixels, that's how many pixels the sensor has. It's 2.4 megapixels for the 174 and 6.4 megapixels for the 178. Where does this come from? Well, if you take the sensor, it has 1936 pixels by 1216 pixels. If you multiply those together, you're going to get 2.4 megapixels. And for the ASI178, it's 3196 by 2080. If you multiply those values together, you're going to get 6.4 megapixels. So you might think, well, gee, the size of the sensor itself, since it has more megapixels, 178 must have a larger sensor size. And we come down and look at the sensor sizes, and we find that sensor size for the 174 is 11.34 millimeters by 7.13 millimeters, whereas the 178 at 7.4 millimeters by 5 millimeters. Why is the 174 has a larger sensor size? Well, that is because the related factor of pixel size, and this is in micrometers. The ASI174 has a large pixel size, a relatively large pixel size at 5.86 micrometers, whereas the ASI174 is only 2.4 micrometers. Does it make a difference? Well, for larger focal ratio telescopes, the larger pixel size wins out or is better or preferred. Next on the list is full well capacity. Now you can think of the full well capacity for each pixel. You can think of it as like a bucket of water. Who can hold the most amount of water before overfilling? And it turns out the ASI174 can hold more charge than the ASI178. So that means the 178 is going to fill up. And what happens is when a pixel fills up with capacity, it'll start going into the pixels next to it. So that means it's going to lead to a little bit of bloating is what it's called. Read noise. The lower the read noise, the better it is. And the 178 has a lower read noise, although for solar imaging, you're not really going to notice that much of a difference. In analog to digital converter, that stands for ADC value. And that sort of was related to up here at the frame rate. The top ADC value for the 174 is 12-bit, and the top ADC value for the 178 is 14-bit. Or the higher the ADC value, the better. It gives you a better dynamic range, but you're hardly going to notice a difference between these two. Quantum efficiency, 77 versus 81%. Those are very close, hardly a noticeable difference. And lastly, the shutter, what type of shutter it has. Well, the 174 has a global shutter and the 178 has a rolling shutter. Now, what does that mean? That means that when it's collecting its data, if you have a global shutter, then the pixels fill up the entire, or the sensor is filled up all at once. Whereas in a rolling shutter, each individual pixel is filled in a line, so it goes across. So it's sort of like a typewriter. One line, then it goes to the next line, then it goes to the next line until the entire sensor is filled up, and then it takes another image. For solar imaging, the global shutter is preferred. Going back to look at which camera would be better for my telescope, I think I mentioned the pixel size. So 5.86 pixel size using my setup would be better than the 2.4 pixel size for the 178. To do that, to demonstrate this, let me show you another program. We're going to use Astronomy Tools, and we're going to go to Calculators, and we'll go to CCD Suitability. And it gives you the theory on why this is. Over here, you can read it yourself. I'm not going to go through too much with that. And it gives you this resolution formula. Basically, it's pixel size divided by the telescope focal length, multiplied by this magic 206.625 value. When you do that, when you plug it in here, you're going to get a resolution, and the optimal resolution, if you have okay seeing, would be 0.67 to 2 arc seconds per pixel. Let's go over this formula real quickly. I think it's kind of interesting. We're going to go through the formula with my ASI174 using the Quark and the ED80. So here's the formula. The resolution is going to be based on my pixel size, which is 5.86 micrometers, divided by the focal length of the telescope, which is 2520, multiplied by this magic number. And if you do this, you get 0.48 arc seconds per pixel. I think that screen prior said you want to have somewhere between 0.67 and 2 arc seconds per pixel. So this is a little bit low, but this value is much better than the 178 that I'm going to show you in a second on that program. I do want to show you where this 206 value comes from. It's actually kind of interesting. Here's another version of the formula. The reason you have to multiply it by this factor is it's because it's a radian to arc second converter. These values are in radians here. And so if you take 180 degrees divided by pi radians, multiply it by 3,600 arc seconds in 1 degree, if you multiply this value right here, you'd get 206,265. Why is it 206 and not 206,000? That's because this is in micrometers, this was in millimeters, but if we convert this to micrometers, we would get, it's basically a factor of 1,000, and if you divided 206,000 by 1,000, you get 206. Oh, going back to this, you don't have to plug in the formula, and if you want to do other things, if you want to do any type of telescope and match up to any type of camera, you can use this really neat program. You just put your telescope in here. I had the Orion ED80. We're just going to look up the Orion ED80. And here it is right here, and it already knows the focal length. There's no Barlow on here, not yet anyways. Oh, actually there is, what I'm talking about. We're going to use the 4.2 Barlow because that's the Quark. And we'll put the camera on here, and we'll put the ZWO 174. Here it is, and it already knows its pixel size. We're going to use one-to-one binning, and here it is, 0.48 arc seconds per pixel. And down here it says ideal pixel size we're seeing, that's what we said earlier. The combination that I had leads to a slight oversampling, but for solar work, it's not really going to make too big of a deal, but it is. They just wanted to let you know that. Okay, now let's put the 178 in here and see what we get. Here it is, 178. And again, it already knows its pixel size. And look at this resolution, 0.2. And here, this combination leads to definitely oversampling, not even a slight amount oversampling. Okay, so based on this data and using my Orion ED80, the clear winner here is going to be the 174. Also, let me just show you here's the two cameras. I have the pictures of the actual sensors on here. And the 178 has a much smaller sensor than the 174, which is a much larger sensor. The sensor size itself is going to allow you to see more of the sun. So if you have a larger sensor camera, you're going to see more of the sun. Whereas if you have a smaller sensor, you're only going to see a smaller portion. So that's another advantage to using the 174 in this case. So now it's time to go over my results, and I have some final thoughts as well. So for frame rate, clearly the ASI174 wins out. For resolution, sensor size, and pixel size, all three of those sort of go hand in hand, but pixel size sort of defines everything else. And for my system with the larger focal ratio of over 30, the ASI 174 again wins out. So for full well capacity, again, the 174 wins out here. It's more than double the ASI 178. Read noise, 178 wins out, but it's not really a big factor for solar imaging, and these numbers are pretty close. ADC value, again, the 178 wins out, but it would hardly be noticeable, especially with solar imaging. Quantum efficiency, these numbers are very close together, but the ASI 178 wins out on that one. And finally, for shutter, the global for the 174 wins out. So at this point, let's go take a look at some of those images that I took with the different cameras. And then I have some final thoughts. Okay, well here is my comparison. I took these images yesterday using both the ASI 178 and the 174. The first one is using the ASI 178. It was a stack of the best of 100 out of 500 frames, no processing, and it came out surprisingly well, I thought. And this little thing right here, that's a spot, so avoid, that's not a sunspot, that's actually a spot on the sensor. I didn't take any flats or anything with these things. And these are these Newton rings, so minus the Newton rings, just look at the rest of the stuff. There is some detail. Here's a spot right here, here's another active region right here. I thought it came out pretty well. Here is that same area taken shortly thereafter using the ASI 174, same best 100 out of 500 frames, using auto stacker to stack them and no processing. But this came out so much better than the 178. Even though the 178 came out okay, as I said, the 178 is a decent camera. It's just not paired well with my setup. Here's that the sunspot that you can see it came out much better. And here's that active region that very clear. And then this, because it has such a larger field of view, we actually get another sunspot over here, and we get another very large active region over here. This is a much bigger sensor than the 178. Okay, now I did a little processing with it using IMPPG, and I brought out the sharpness a great deal on this 178, so it looks even better now. And this active region here came out much better, and I've actually brought out some of the solar prominences here that you can see. Here's that same image, almost identical processing that I used on the 178, but again, this is much clearer. Look at these little prominences coming back on themselves. The detail on this sunspot, this active region here, and this large active region here, it's just very good. All right, and then my final bit of processing that I usually do, I put some color in using Photoshop and a couple other things. And again, it came out pretty well, the surface details on here. But let's take a look at what I did with the 174. And again, it's very, very good. I was very happy with how this came out. Okay, now I'm going to show you some other images that I took 4 years ago with the 178 and some recent images with the 174, but I'm not going to do any discussion. I'm just going to show you the image. Please enjoy. Final thoughts, and this is going to apply to any solar camera. I sectioned it off into most important and stuff that would be helpful. First off, make sure your camera is mono version. Make sure the pixel size matches the focal ratio, and make sure you get a camera with the highest frame rate possible that you can afford. Things that would be helpful. Well, if you get the full well, make sure you have a larger full well is better. Read noise, lower is better. The ADC 12 versus 14, most solar cameras are going to be 12. 14 would be preferable, but it's not really that big of a factor. You'd hardly notice a difference. Quantum efficiency, in this case, the higher value is going to be better. And for the shutter, if your camera is has a global shutter, all the better, although other astrophotographers, solar astrophotographers have said that it's really not such a big factor. Other ZWO solar cams, good solar cams out there that I didn't talk about was the ASI290. That has a 136 frame rate per second, and the pixel size is 2.9 micrometers. They also have a new camera out there that's the ASI432, and that has 126 frames per second, but that pixel size is 9 micrometers. This one would probably be a better fit for the Quark. And lastly, I have a resource that I want to share with you guys that I'll put a link in the description section. It's AZAstroGuy and how to choose a solar camera. He does a fantastic job and goes into some of these characteristics much better than I do, and he's actually a solar expert. I'm going to put that link in there so you might want to check his video out, and he does a lot more of these cameras. Okay, well, thank you very much. I hope you enjoyed this, and we'll see you next time.